Hello, hello. Today's lecture number 8. All right, so we're going to consolidate our concepts on diffraction from crystals a bit further. All right, the first point I would like to quickly recap is the evolved construction. So things are really neat in the evolved construction. First of all, you define a direct lattice, some direct lattice, from where you have A and B translation vectors. Suppose this is our cubic lattice primitive. From here you define the reciprocal lattice. A star, B star, other translation vectors. If the direct lattice is primitive, the reciprocal is also primitive. You define the direction of the X-rays. For example, this is our X-ray direction. This direction carries over into the reciprocal space. And then you take the entire reciprocal lattice, which is a sequence of squares, and position it onto the direction of the X-ray so that what you would really like to do is you could start off by drawing a circle of radius 2 pi over lambda. Anywhere on your paper you draw a circle of radius 2 pi over lambda, and then you take your reciprocal lattice, and without turning it around, you position your reciprocal lattice so that one of the points coincides the exit point of the circle. So in our case this is very simple. The reciprocal lattice itself is a square grid correct? So this point where the X-ray is exiting the circle, the reflection circle, this point is labeled 0, 0, 0 in the reciprocal plane. All other points are labeled accordingly. So this would be the point 0, 1, 0, 0, 2, 0, 0, 3, 0. This would be 1 bar, 0, 0, and so on. And remember that at the moment we're looking at only one plane in the reciprocal, in the three-dimensional reciprocal space. So this is just one plane, and all of these reciprocal lattice points have their L value equal to 0. That's how we've drawn it. So this is the HK0 net in the reciprocal space. We'll also have an HK1 net, an HK2 net, an HK1 bar net, HK2 bar net, because the reciprocal space is three-dimensional. Okay, and then in order to see the allowed reflection directions where scattering is taking place, we look at the whether this evolved circle, it's really a sphere, but in this net it looks like a circle, cuts at points where there is an intersection between the circle and the reciprocal lattice points. Okay, suppose these are the points of intersection, then it really means that the crystal is placed here and the reflections are occurring in the directions shown. Okay, and we looked at this in the previous lecture. All of this is consistent with the Bragg formulation as well. And these angles, so this is the incident X-ray direction. So angles of the scattered or reflected rays as measured from the impingent X-ray direction, they are 2 theta. So reflections occur at these 2 theta values in this plane. From these planes, a reflection is going to take place, and the blue lines are the physical directions of the X-rays. So X-rays shine and they go out, fan out in all of these theta directions. And here we're talking about a single crystal for the time being. Okay, so this is the evolved construction, and it's consistent with Bragg's formulation. Now, but this reciprocal lattice is really three-dimensional. So if I have, say, let me try to draw. This is a reciprocal lattice net in 2D. There is going to be a corresponding net just above it, right? And a corresponding net just above it. So if I look at this from the side, there is a net here, a net above it, another net above it, and I'm drawing just these wavy lines for visual clarity. So this could be the HK0 net in the reciprocal space, the HK1 net, and so on. We also have the HK1 bar net, and so on. So it's a three-dimensional stacked structure in the reciprocal space. Now this evolved sphere is three-dimensional as well. So not only do scattered X-rays emerge horizontally, in the nets above and below there is going to be an intersection of the evolved sphere with the reciprocal lattice points. But the diameter of this sphere is maximum somewhere. So if I go to a higher plane in the reciprocal space, it's still the same grid. This is our reciprocal lattice. Let's say this is the HK1 net. Now if I were to draw the reciprocal sphere on this net, so the sphere of course is the evolved sphere, looks like this. It's 3D, right? And there is a net here, a net here, a net here, and so on, depending upon the size of the reciprocal lattice vectors, which in turn depends upon the size of the direct lattice. So there are nets everywhere. Then there are nets that are exclusively outside the evolved sphere, and the evolved sphere never intersects them. So no reflection from those planes will ever occur. Okay. So now if you're above the HK naught net, and if you take a view of the evolved circle in that net, the circle is going to be smaller. It's not going to be at its full diameter. So you'll draw a smaller circle. Now if there is a point of, now this point is here, this exit point from the circle coincides with an X-ray. But here the exit point does not correspond with an X-ray because this point is slightly above the HK naught net. But still there could be some points of intersection between, say, this point here, between the evolved circle in this plane and the reciprocal lattice points, and X-rays will be scattered along those directions. But suppose this is the HK1 plane, HK1 net. In that case, suppose I have this point, the X-ray will not go out in a horizontal fashion, it will emerge out at a certain direction above the horizontal. So it's going to come out here, come out from here. Okay, so I'm not drawing the full ray because it's not horizontal, this is going to come out at some angle. Okay, but nevertheless, wherever there is an intersection between a reciprocal lattice point, which corresponds to a plane in the direct lattice, and the evolved sphere, there is going to be scattered X-ray. So there are X-rays coming out in all directions, in the horizontal plane, different angles, above, below, and so on. And wherever this evolved sphere intersects with the reciprocal lattice point, there is going to be a scattering. There is going to be a reflection from that particular plane. Any questions about this? So there will be no scattering. All of those X-rays will pass unimpeded, without scattering. So this construction helps us find out what are the scattering angles. And it is the reciprocal lattice, the geometry of the reciprocal lattice, that tells us the directionality of scattering. What thetas do we scatter at? What two thetas do we scatter at? Okay, the amount of scattering, the intensity of each of these scattered X-rays is yet undetermined. That's going to be our next lecture. But at least we know that there are certain directions over which scattering is going to take place. Now I can use a cubic lattice, I can use monoclinic, hexagonal, I draw the corresponding reciprocal lattices and follow the same process. Now I can do different things. I could change the wavelength of the X-ray. I could, now the sample is here. The sample is located here. The sample size is really, really small. So whenever X-rays, when you're doing a real experiment, you have some kind of camera, some kind of detector around the sample, which is picking up these X-rays from different directions. Okay? And you could also do a few things. For example, if I were to rotate the sample goes around and around and around. What's going to happen? This entire reciprocal lattice is going to rotate. Okay. You could also oscillate the sample. It goes either way. You could rotate the X-rays. Okay, so in the original experiment, and it's possible that you do not get any scattering as well. Planes that have large indices, large Miller indices, they might fall outside the evolved sphere. You don't get any scattering from them. Okay? Now, and do remember that the proper process has to be followed for determining the reciprocal lattice. Okay, you look at the planes and you find the normals to those planes, or you can use the formula as well. Now let me just as an interesting insight, when Lowy, he preceded the Bragg family, when Lowy did these experiments, he in fact shown white X-rays on the sample. White X-rays are X-rays that have a range of wavelengths. Okay, so instead of passing monochromatic X-rays, he shown white X-rays with a range of wavelengths. So what would happen in that case? So if I draw, say, let me now move away from the cubic system, let me draw some, for example, monoclinic reciprocal lattice, say like this. Okay, this is the reciprocal lattice corresponding to the monoclinic lattice crystal system. Let's suppose this is our direction of X-rays, right? So I take any point and use this to be demarcate this as my exit point of the evolved circle. So I draw a circle of radius 2 pi over lambda for a particular wavelength. I'm at a certain net, one net of the reciprocal space. Now if the wavelength changes, if the wavelength say becomes bigger, what's going to happen? The radius shrinks. So the radius shrinks, keeping the exit point the same, because all of these X-rays are shining at the same time on the crystal. So I don't want to change the exit point in the reciprocal evolved construction. So if the radius shrinks, I get another circle here, right? This point being my fulcrum fixed. So I can get this shaded region which is bounding the evolved circles inside this plane. And since this is a continuous spectrum of X-rays, so if I look at the spectrum of X-rays, I plot lambda here and the intensity of X-rays, suppose they are between two bounds, some lambda 1 and lambda 2. So one of the circles will have radius 2 pi over lambda 1, the other will have radius 2 pi over lambda 2. So there will be some region in between, and it's a continuous spectrum. So all the reciprocal lattice points, all of them inside this green shaded region will cause a reflection, right? Because invariably they will coincide with this region, they lie inside this region, because and all evolved circles are present inside this region, all of them, it's continuously filled. So all of these reciprocal lattice points will contribute to scattering, they will scatter off radiation. All right, so you will get scattering in all different kinds of directions. Another subtlety I would like to highlight is when we write down the Bragg formula, 2d sine theta is n lambda. So far we've taken n to be equal to 1 in our discussions. Now suppose I have if I draw the direct lattice, and it's cubic, suppose A, B. Suppose this length is A. Now there is scattering can only take place whenever a plane is occupied by atoms. Okay, so there's a plane of atoms here, and if I move along the A direction, the next plane of atoms is here. So this, as we all know, is the 1, 0, 0 plane, Miller plane. When we draw the reciprocal lattice for this structure, since it's cubic, each one of these lengths of the reciprocal lattice vector is 2 pi over A. Suppose this point is 0, 0, 0. The next point, the first point that is encountered is 1, 0, 0 in this direction, 0, 1, 0 in this direction, and then you add up the indices and so on. So this is 0, 1 bar 0, 1, 1 bar 0, and so on. So you get all the reciprocal lattice points. Now if I were to take, so for this plane spacing is d 1, 0, 0. So I can write down the Bragg formula d 1, 0, 0 sine theta, let's say n equals 1, this is lambda. So this is a Bragg reflection condition. Okay. Now suppose I have some fictional plane. This fictional plane, no atoms exist here at the moment. It's a fictional plane with Miller indices 2, 0, 0. It's not a true lattice plane because there are no atoms here, so I wouldn't like to put the parentheses. So I just call this the 2, 0, 0 plane. It's halfway in between, and it's a primitive unit cell, so there are no atoms here. Everything has been defined with respect to these lattice planes. Alright, so I take this I take this plane in between. Now the spacing between, so the 2, 0, 0 planes are here, 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 here. So the spacing between these planes is d 2, 0, 0 is half of d 1, 0, 0. Okay, so what I could do is, if I were to write the Bragg formula, 2d 2, 0, 0 sine of some theta, some other theta, theta prime, equals lambda. So I consider the first order reflection from the d 2, 0, 0 plane. Because I put n equals 1. Alright. So however, I do know that this object here is half of d 1, 0, 0. So I replace this by here, still have theta prime and lambda here. Okay, this would make 2 times d 1, 0, 0 sine theta prime is 2 lambda. So if I compare this equation number 2 with equation number 1 over here, they're exactly the same. So it's they will be the same. If I put n equals 2 here, if I put n equals 2, I will get the same left hand side provided theta equals theta prime. So this means that a first order reflection from this reflecting plane, a first order reflection from this reflecting plane, which is not a true lattice plane, this plane here in the middle, gives the same scattering angle as a second order reflection from the original lattice planes. Okay, so a first order reflection from this 2, 0, 0 reflecting plane is the same reflection as a second order reflection from the 1, 0, 0 planes. Okay, so it's unnecessary to include this reflecting plane. Okay, higher order reflections, this reflection by the way is going to occur at a different theta, right? Because the formulas, one of the formulas has 1 here, the other formulas are 2 here. So higher order reflection from these planes, which are equal to first order reflections from the planes in between, are going to necessarily occur at different angles. Okay, so this is a subtle point that I just wanted to mention, and I'll highlight this in a homework problem as well.
So theta prime is not like a integer multiple of theta, right?
No. This is a non-linear equation.
What do you mean when you say different orders of reflection on the same plane?
So this is our formula, the Bragg formula, and this is valid when n is 1, when n is 2, when n is 3. When n is 1 it's called first order, n is 2 is called second order, n is 3 is called third order. Path difference change हो रहा है. So in one case, suppose the X-rays are scattered like this, a higher order reflection may scatter them like at some other angle. Okay, but you cannot have arbitrarily higher orders, because this sine theta here has to be less than 1. If you keep on increasing this, the right hand side is n lambda over whatever d there is. So if you keep on increasing this will go beyond 1. So you cannot have arbitrarily high orders. All right, and the intensities might also go down. All right, now what I would like to highlight is another subtlety. If I were to take, say, when we do transmission electron microscopy experiments with electrons as our probing radiation, electrons, as you know, can have a very big very short wavelength, so a very large evolved sphere. So if I were to take a reciprocal lattice and points on the reciprocal lattice, say these are my points of interest, suppose this is 0, 0, 0, 1, 0, 0. I suppose this 2, 0, 0, this would be 1 prime 0 0, 1 prime, oh this is my label ऐसे किया, this is 0 1 prime 0, then I have 1 1 prime 0, this is 2 1 1 prime 2 0, 1 and so on. यार एक मिनट, ये है 0 0 0, ये है मेरा 1 0 0 2 0 0, this is 0 1 prime 0, this is 1 1 prime 0, this would be 2 1 prime 0, this would be 3 1 prime 0, and so on. Alright, so this is my reciprocal lattice. If I have a really large evolved sphere, the curvature like this, because extremely energetic X-rays, electrons, extremely short wavelength, then what's going to happen is that neighboring points near the exit circle, this is my exit circle for the electrons, these neighboring points in a row of the reciprocal lattice, all of them will lie roughly on this evolved circle, because the evolved circle turns very slowly. So all of these points on a row will lie on the evolved sphere. So these points are all H00 points in a row, not even a net, it's just one row of the reciprocal space. So all of these points will give scattered radiation. If I have some kind of detector placed at the bottom, and I also have a magnification for the electrons, so the electrons are coming at small angles, and I want to do some kind of magnification for electrons, so I put an electron microscope which can magnify electrons through different kinds of lenses. And lenses for electrons, of course, are not like optical lenses, they are electromagnetic fields. And I do a microscopy, I can look at the scattered radiation, and the points will be kind of spaced far apart depending upon the magnification. So I will get dots or patterns which will correspond to reciprocal lattice points. So this point could be 0 0 0, this point could be 1 0 0, 2 0 0, 3 0 0, 1 prime 0 0, 2 bar 0 0, 3 bar 0 0 0. I will get a point here which is 0 1 prime 0, 1 1 prime 0, 2 1 prime 0, 3 1 prime 0. I'll get a point here 1 0 0, 1 minute, 1 1 0, 2 1 0, 1 prime, 1 1 prime 0, 1 2 prime 0, and so on. So I'll get a host of points. क्या? चलो कोई बात नहीं, इतनी छोटी आप खुद कर लो. So you'll get all of these points in this region will give scattered radiation. And then there will be a gap. There will be some gap because now the evolved sphere has moved out, and then it will hit points at some other row. Okay, so there will be a gap here. So when you look at this overall, you will have some collection of points followed by empty space and then another ring of points. Okay, because now this evolved sphere is going out. When it has kind of diverged from this row, it is not intersecting with any other reciprocal lattice points in the second row. It might intersect with some lattice points in the third or the fourth row. So you'll get another ring when it circle reaches there. Okay, so you'll get zones inside your diffraction pattern. A zero order zone followed by a ring, and this congregation of points is a direct visual signature of the reciprocal lattice. So you can see the reciprocal lattice in a transmission electron microscope. Of course, you can see the direct structure as well. The microscope can operate in two modes. Either you see the reciprocal space or you can see the direct space. Okay, so these techniques come from optics. All right. Now the last point, since it's a short class, the last point I would like to mention is, if I consider the BCC lattice in direct space, now this is a direct space lattice. So I will have, if I draw the lattice, body centered cubic, there is a point in the body center. So this is the I lattice. So this point is 0, 0. This point is 1, 0, right? This point is half, 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 the fractional coordinate of the body centered point. Now the first, if I were to draw the reciprocal lattice for this, now this is a homework problem number 2. The reciprocal space to an body centered cubic lattice is a face centered lattice. ने तो होमवर्क नहीं किया, ये तो हमने बात की थी ना. The reciprocal, the Fourier transform of a body centered lattice is a face centered lattice. The Fourier transform of a face centered lattice is a body centered lattice. Please do attempt this homework problem, and I have given you hints in that question on how to solve it. Now if I look at this from a perspective, so I'm looking at this from the top. This is my cubic cells. There is a point here, point here, point here, and a point here. And then there is a point at elevation 1/2. And the lattice planes, so there's a lattice plane here, a lattice plane here. There is also going to be a real lattice plane over here. Okay? This point is at a certain elevation 1/2. So if I were to draw the reciprocal space for this lattice, this is the 2, 0, 0 plane. Now it's a real plane, isn't it? This is a 2, 0, 0 plane. So if I start moving from my 0, 0, 0 point in the reciprocal space, the first point that will be created, that will be encountered in the reciprocal space, is the 2, 0, 0 point. So if I were to draw the reciprocal space corresponding to the BCC lattice, I will have 0, 0, 0 point followed by 2, 0, 0 point. So the first point that will be encountered is the 2, 0, 0 point. Okay. Similarly, in this direction, 0, 2, 0, this point will be 2, 2, 0. And I will also encounter a point at the center of this face, which is 1, 1, 1. So if here I were to draw the 1, 1, 1 plane, the 1, 1, 0, 1, 1, 0. This is 1, 1, 0. So what's the 1, 1, 0 plane here? It's this plane. And an atom exists inside this plane. Correct? So as you start moving away from your origin in the direct space, and you want to find out at what plane do you encounter an atom or a point or a lattice point or a valid lattice point. We're not talking about atoms, valid lattice point. So you move to the 2, 0, 0 plane. From here you move here, you will encounter an atom which is at the body centered position inside this plane. So your first move inside the reciprocal space has given you the point 2, 0, 0. The same can be true for the B star direction. Okay. Now let's move diagonally. Let's try to move diagonally. There is no 1, 0, 0 point here. All right. Now what that will be a reflecting plane and a non-lattice plane. You can always define that plane, but that does not qualify to be included in the reciprocal lattice for the BCC system. Now if I move along the diagonal, I encounter this plane which has been shown to you in this direct structure, and there is an atom in that plane, and this plane is the 1, 1, 0 plane, isn't it? So there is now a point in the reciprocal space at the location 1, 1, 0. So this is a view of the reciprocal space corresponding to the Fourier transform of the BCC lattice, and you observe that this is face centered. This has a point at the center of the face, and look at how we are counting the points. So from 0, 0, 0 you go to 2, 0, 0. So you jump in steps of 2 along the edges, and you jump 1 unit along each edge along the diagonal. You get another point. And then you repeat this in 3D, you'll get a face-centered lattice. So this body-centered lattice in the reciprocal space will be a face-centered cubic lattice. It's not nice to call this a lattice per se, because technically it's not a lattice, but the word lattice is just a misnomer. Okay, so a body centered lattice in the direct space gives you a face centered lattice in the reciprocal space. Now from the perspective of X-ray diffraction, if I repeat this will be 4, 0, 0, this will be, here will be 4, 2, 0, this will be 3, 3, 0, and so on. So if you look at all these reciprocal lattice points and I put an evolved sphere onto this reciprocal lattice, I can only get reflections from planes which have HKL values such that the sum of their HKL values is even. Right? 2, 0, 0, the sum is even. So H plus K plus L, if it's even, a reflection is possible. If I have a body-centered lattice, no matter what the motif is, no matter what kind of atoms are juxtaposed on the body-centered lattice, from a diffraction perspective, I can get peaks or scattering only from planes when H plus K plus L is an even number. See, all of these points qualify for this. And if you look at the space group tables that have been provided, and you look at IM3 bar M, space group number 229, on the rightmost there is a column that says diffraction conditions. Reflection condition is the rightmost column, and for I m 3 bar m, which is of course body centered, for general points the condition for reflection is h plus k plus l is 2n. So if you look at the peaks that are coming out from a diffraction experiment, first of all the experiment will give you thetas. From those thetas you have to infer the HKL values. This is called identifying or indexing the peaks. You have to index the peaks. You have to tell which peak corresponds to which plane, to which reciprocal lattice point. And I'll show you an example for this probably in the next class. If those HKLs are such that the sum of the H, K and L is always even, then your original lattice, the structure has a lattice which is body-centered cubic. Likewise, if you start off with a face-centered cubic lattice which has points at the centers of each of these faces, you do a reciprocal lattice for that, you will get a body-centered structure. So you'll get the same point 0, 0, 0, 2, 0, 0, 4, 0, 0, but this point will be at the center of the body at 1, 1, 1. Okay, and for those, and you can find out that those points exist for which all the indices, the planes give reflection for which the indices of all the planes are either all even or all odd. All even or all odd. So 1, 1, 0 is not permissible. 1, 1, 1 will give you a reflection. 2, 3, 0 is not possible. 2, 2, 0 is possible. 1, 3, 3 is possible because they are all even or all odd. And if you look at the reflection conditions that have been specified for the space group Fm3 bar m, next page, the reflection conditions are mentioned here. They are mentioned that H plus K, H plus L, K plus L, each one of them is equal to some 2 times n. Each one of them is even, which is another way of saying that all of the indices can be even or all of them can be odd. So by looking at, when you index your peaks, you can tell, and if it's a cubic system by the way, which is only one of the 7 crystal systems, you can tell that whether it's body centered or face centered. Okay. For the cubic system, if you look at the HKL planes, the distance between HKL planes, which is D, is given by H bar square plus K square plus L square over A square, right? This is for the cubic system. And you can draw HKL planes in the cubic system. You know the indices HKL, and you can find out the distances between those planes from simple geometry or trigonometry. Okay. For example, the 1, 0, 0 planes, which are the faces, you put H1, 0, 0, 1 over D square is 1 over A square, so the spacing is D is equal to A. And this applies for body centered, cube, face centered, primitive. This is true for cubic. If I have this plane over here, which is the 1, 1, 0 plane, and then I take the neighboring plane, the neighboring 1, 1, 0 plane, the distance between these planes is going to be 1 plus 1 plus 0 A square 1 over d square, and this means that this is going to be d equals a over under root 2. This is the distance between these planes here, okay, which are inside the cube. Okay, so this formula is valid for the cubic system. Now we also know that 2d sine theta is lambda, which means that sine theta is lambda over 2d, which really means that sine square theta is lambda square over 4d square. Now 1 over d square is this. So if now what a spectrum looks like is the following: you have thetas here and you have some intensities of X-rays as a function of theta. In fact, you have 2 theta here. You plot generally with respect to 2 theta. So you get a spectrum. You get some peaks. And I'll show you some real spectra. Now in this case, you identify the thetas or the 2 thetas at which peaks occur. You find the positions of those peaks, right? So you get a table of thetas. So this is the first step in determining crystal structures from X-ray data. You get a table of thetas. Then you can find the sines of those thetas. So you get a table of sine theta squares. Now on the right hand side, everything is unknown. You just know lambda, you know the wavelength of your X-rays. But you do have a few clues. First of all, you do know that this has to be an integer. Correct? And this is some number. So you do know that sine square theta is, अगली क्लास तो नहीं आ रही, बाहर हरकत तो नहीं, sine square theta is some number, arbitrary number, n is an integer, and there are certain allowed values of n only, which correspond to h square plus k square plus l square. For example, you cannot have 7 in this. You cannot have 15 in this. You cannot have 23 in this. Certain allowed values of n. If all your sine square thetas match this pattern, then you can determine A and you can determine n. So this has to be a search process that is done. Okay, and from n, once you have n, you can determine your planes which are reflecting. Once you know that, you can determine capital A. From capital A, you can know the dimensions of the cell. And all of this works only for the cubic system, by the way. However, you can see whether the HKL planes that are reflecting, if they follow the conditions, the absences that we have, certain reflections are absent for face-centered cubic. For face-centered cubic, you need to have them all even, all odd. If you have mixed indices, those reflections are absent. These are called systematic absences. Body-centered, they must all add up to odds. All evens, all odds are systematically absent. So you can tell this dimensions of the cell, how big is your unit cell, and you can also tell the kind of Bravais lattice as well. You can't tell which atoms are there for the time being inside the cell. Whether it's iron, copper, aluminum, molybdenum, you can't tell that unless you also look at the intensities of these peaks. That's the next step, which is more daunting, more overwhelming, but it's routinely done. So just to give you an example, let me see if this cesium chloride. Okay, the first column shows the values of sine square theta. Peaks occur here. You do a diffraction experiment, peaks occur here. Now this sine square theta, if it equals A times n, I need to find A and I need to guess n. So n is sine square theta divided by some number. So n is an integer. So I try out different integers. So suppose my n equals 1. So I divide sine square. So I want to choose. So if I divide the first sine square theta by 1, I get this. This is my candidate A. Just to give you a simple example, this is my candidate A, and then I take this sine square theta and divide by this A. And repeat this for all the sine square theta. Luckily, bingo, I get integers for n. Okay, so now what I've done is I've not arbitrarily, but I've chosen some A. A, of course, is sine square theta divided by some integer. So I can do a search. I can first see if I put n equals 1, if my A equals sine square theta over 1, then for that A, would I get integers for all the other reflections? That's what I've chosen, and luckily I do. So this capital N does not have a forbidden number. There's no 7 here, for example. So this is valid. So now I have found out A and I found out N. I've actually solved my problem. I need to identify the peaks or index the peaks. I'm getting peaks at these values of theta. I need to tell which planes or which planes in the direct structure are they coming from, or which point in the reciprocal space are these peaks coming from. Okay, so that is simple to do. N equals 1. N, of course, is h square plus k square plus l square. So it's evident that this could be the 1 0 0, which is the same as 0 1 0 or 0 0 1 because it's cubic. 2 is 1 1 0. So I can immediately index the peaks. I can tell which peak is coming from which reflection, which plane is reflecting. Okay, 3 is 1 1 1, 4 is 2 0 0, 5 could be 2 1 0, 6 could be 2 1 1, 8 could be 2 2 0.
Sir, all even your all odd color conditioning है ना?
No, क्यों? वे तो देखना वो बाद में देखेंगे. Now you have indexed your peaks and everything is mixed here. So it's neither primitive, it's neither body centered. It's neither body centered nor face centered cubic. It's primitive. And this is the structure of cesium chloride. Okay, if I know the wavelength of my X-rays, I can find out the dimensions as well, because my capital A is now lambda square over 4a square. So I take the square root of this to find out my cell dimensions. So my cell dimensions is that I have a cubic primitive cell for cesium chloride with dimensions 0.41 nanometers on each side. So this is how I have indexed all the peaks in the diffraction pattern from cesium chloride and found out this just the lattice parameters A, B, C, alpha, beta, gamma, and the size of the unit cell. I do not as yet know what's inside, which atoms are there, because for that I need to know the intensities of these peaks. And by the way, intensities are difficult because intensities are the modulus square of kind of fields. Lots of information, phase information is all lost, and we're talking about rays here. So this phase information that is giving us this interference. Interference means this constructive interference only along a allowed scattered direction. So phase information is lost. So this phase retrieval makes this problem really difficult, but it's routinely done. It's difficult but not impossible, and it's become so commonplace these days that computer programs, a plethora of computer programs exist for crystal structure determination. To give you another example, let's look at copper. Now I'm going to just kind of, for the time being, delete all the information. Copper, let's see what kind of structure copper has. And now assuming it's cubic. Okay, you always start off with some preconceived notions. Okay, so I want to find out capital A. So my test for A is I take all of the sine thetas are assorted in the ascending value, so that's important. So I take my first, okay, my first sine square theta, and I divide by 1, and then I take this sine square theta and divide by my value, my proposed value of A, and see, repeat and see if I get integers. I don't. So this is not good. So now I divide by 2 instead and repeat. I still don't get integers. So and now let's divide by 3. Now I do get integers. So now I have found out capital A, and now none of these integers, none of the values of n contain a forbidden n. So it's fine. I've actually almost solved the problem. I need to now index the peaks. So 3 corresponds to, say, 1, 1, 1, 2, 0, 0. 8 is 2, 2, 2. You can already tell it's face centered cubic. 11 is 3, 1, 1. Okay, 9, 10, 11. It doesn't matter whether you write 3, 1, 1 or 1, 3, 1 or 1, 1, 3 because it's cubic. 12 भी इसी तरह कर सकते हैं. 2, 2, 16 कर सकते हैं. 4. There's no mixing of even and odd, so it's face centered cubic, and it's cubic. We already know that. We've already sealed that. Now we're sealing the fact that it is face centered cubic. Copper is face centered cubic. It belongs to FM 3 bar M space group. 19 का क्या होगा? 9.
3, 3, 1. 4, 2.
Okay, and the A dimension. Okay, likewise for iron. Now if I repeat this for iron, अब थोड़ा सा मैंने वेवलेंथ भी बदल दी है इसकी. खामोशी है. The problem with this is that I get 7, which is not allowed. So I have to test something else. I have to go to higher orders. This looks fine. And I've already I think solved this already. 6, 2, 1, 1, 4, 5, 6, 2, 4, 3, 9, 10. So this is the solution, and the sum of H, K and L is always even. Okay. So this is body centered. Iron is indeed body centered. Now if I have tetragonal or orthorhombic or hexagonal, probably I'll give that as homework. There are other formulas that you need to remember. Machine has headers and all, but I've saved this data as a text file. So the first column are the values of 2 theta. Second column are the intensities of X-rays. And I can plot this data. So the machines can give you a very fine resolution, 10.00, 10.02, so it's 20 milli-degrees resolution at which this data has been taken. बार स्टूडेंट्स आ गए हैं, ठीक है. So I plot this. So this is what the data looks like, ठीक है. 2 theta on the x-axis and intensity is on the y-axis. All right. So now you put a peak finding algorithm to find out the location of these 2 thetas, and then use your computer programs to index the peaks. So we'll continue on Tuesday, inshallah.